Excellent. Yeah. Thank you, and thanks so much for having me here today. I'm from TU Wien and IC Austria right now in the transition process between two different institutes in Vienna. But today I would like to talk about some results that we achieved in the group of Marcus Greiner and at Harvard, where I did my postdocs. I would like to start with this. It was a fantastic collaboration with Eugene Demner and Dries Sells on questions of non-equilibrium dynamics and many-body localization, and particularly about the stability of those. And just as a quick reminder, when we talk about MDL, what we think about is we start from an Anderson localization system. So we have a disordered system, and we now let particles in our lattice version of that. We let particles off, and as long as they're non-interacting and it's not disordered, it would be a simple quantum walk. But as soon as we now start to add disorder, we get exponential localization of these particles to their initial sites. Now again, it gets a bit more complicated once we start to add interactions. And the question arises whether these interactions are now giving me sufficiently channels for these particles to not exponentially be localized anymore, but actually rather delocalize. And in the end, the tale of many-body localization is a question of two competing exponentials. On the one hand, I have, as I increase my system size, I have exponentially large Hilbert space and therefore exponentially many states that could potentially couple to my exponentially localized particles. So on the one hand, I reduce my Hilbert space by having localized orbitals of motion such that particles cannot couple to many states. On the other hand, I add more and more sites or particles that add more and more states that could potentially couple to my localized particles. And it's a priori not completely clear which of the two will win. And we had some theoretical developments over the time that suggested, yes, indeed, actually MBL should win and localization should persist, at least if I go beyond a certain threshold of my disorder strength. So in contrast to an Anderson insulator that would actually be localized for arbitrary disorder, here we need to overcome a certain threshold. And it gets much more general than that, because if I have now a system that can be localized, an interacting system that can be localized, I break one of our central ideas of physics, namely in thermodynamics and statistical physics, that all interacting systems generically, or typically, they would reach thermalization. And MBL is now the one exception that would preclude that. That would be an exception to that kind of paradigm. Now in our experiment, we were trying to see this phenomenon, to verify that this actually can happen. The system looks as follows. So we have a quantum gas microscope where we can detect individual particles at sites. Here, in contrast to a transit experiment, we have tunneling between all of those sites, and we load bosonic atoms. So we have a bosonic statistics that are typically repulsively interacting, the Boson-Hubbard model realization. And we can, on top of imaging, we can also project any kind of potentials to make the tunneling inhibited in certain ways or modified in certain ways within this lattice. And we can do all of this projection and imaging with a very high resolution on the individual lattice sites. So we developed this certain quench protocol to probe MBL. And what we do is we start with a mod insulator simply because it's a perfect register for us. So we have exactly an unentangled state of exactly one particle on each lattice site. And for us, that gives us a perfect starting point to cut out certain initial states that are unentangled, simply because the mod insulator is unentangled. Or in a state that we chose here, one-dimensional chains of n atoms, typically 6, 8, 12, depending on the experiments. And then we inhibit tunneling along the vertical direction here. And we also build a box around such that particles cannot tunnel beyond exactly the system that we cut out. And at this point, tunneling is very weak, essentially zero, because we are in this not insulating state. But what we can do now is we can start to switch on tunneling very rapidly. And what it does is that it starts a Hamiltonian evolution under this Boson-Hubbard Hamiltonian that is very far away from the ground state. So we generally will end up in some state that's very far from equilibrium. And after a certain evolution time, we can probe the system, and we usually suffer from parity projection in these quantum gas microscopes. So we will not get the full information of the state, but what we do then instead, we let them tunnel along the orthogonal direction, and then right before the detection, and then we detect afterwards. And then by counting all the particles in each column, we can reconstruct the exact Fock state on which we projected with this measurement. So this is going to be our main observable. Essentially, we are taking samples in Fock space of our many-body state after various evolution times. Here's the model. So we have indeed a Hubbard model here, stable hopping in 1D. We have repulsive on-site interaction, and then we have a disordered potential that we project here, which in this case we actually chose a quasi-periodic potential.
If you had a party interaction, you still reconstruct the localization.
If we had said
active interaction.
Yes, you could also reconstruct that, yeah. So during this protocol, you can also break pairs and then use them afterwards. Yeah. It's difficult with our specific bosons to get attractive interactions, but in general. So one important observable that we can now do is we can look at local observables and check if, despite this unitary evolution in the system, they actually would be described by thermal equilibrium. And one of those observables would be associated to the, so when I look at a single lattice site, the degree of freedom that I have on this lattice site is the particle number. And initially I start with exactly one particle number, with exactly one particle per lattice site. Since that's the unentangled state that I started with, the Mott insulator. But now over this dynamics, this site may become during this evolution, it will be in a superposition of different particles on this lattice site. So there will be a certain statistics that is, for example, like this. So in this case, this would be the histogram of detected particles on the individual lattice sites after a long evolution time, in this case, 100 tunneling times. And you see that having one particle is an option, and it's still the highest chance. So we have a probability of one particle, to measure one particle on the site, that is very different from what I would expect from a thermal statistics. Yeah, so we don't find the thermal histogram here. So the bars here are theory, and the little dots here are experiments. So this very much matches with what we expect in from theory. This is exact diagonalization theory. And we can do this for different evolution times. And what we find is that after about a tunneling time or so, we start to settle. And then if we measure for several hundred tunneling times, there's no evolution anymore. We really reach a steady state. And the steady state, importantly, is far away from a thermal equilibrium. So this entropy, with which we quantify this histogram here, is very far away. This entropy is actually the full entanglement entropy on the single site, because that's really the only degree of freedom that I have on this individual site if I have my global particle number conserved. So this means that we really capture all the entanglement with this observable that this individual site has with the rest of the system. The story now changes if I go away from an individual site and if I have larger subsystems, because they have more degrees of freedom. And if I then look at the entanglement entropy of the subsystem, I can actually divide it into two different parts. The first part is what we call the number entanglement. That would correspond to particles hopping across the subsystem boundary and thereby creating a superposition. That's exactly what we seen earlier. So if I then count my particles in my subsystem, I will count a different particle number each time I would measure, and therefore there is entanglement in the system. There's a second degree of freedom, and that involves no hopping across the boundary, but then involves the configuration of these particles within the subsystem. So I could, for example, have two correlated particle hole pairs here, one on the left and one on the right. So if I now would trace over the right part of my system, I still would see entanglement, even though no particle has actually crossed the subsystem boundary. So we call this the configuration entanglement. And that tells us that the story is not over yet with this steady state local entanglement that I've shown you on the previous slide. In fact, this was also pointed out by other people much before. So for example, here these are calculations by Jens Bartesen for a spin model, which also shows the very same behavior. Yeah? So I have my initial rise in the entanglement, and then at steady state, if I'm looking at the non-interacting system, there would be the blue line here. But if I have interactions present in a system, that I get this very slow logarithmic growth here. That now depends on the strength of the interaction, but is always present and will go on indefinitely, at least for very large system sizes. And what's interesting is that I can indeed separate these two degrees of freedom completely if I have a globally conserved quantity, in our case, the atom number. So I can write the total entanglement entropy as a sum of the number entropy and the configuration entropy. And to probe now that really there's many effects present in the system, what I have to look for is this correlation, configuration entropy. And the way we probed this, the way we detected this was now to look at correlations between these two different subsystems. So what we would do is we would take our snapshots, we would look at subsystem A and subsystem B, and now look at the probability to detect a certain configuration at A together versus their individual probabilities. And if we now look at all different configurations that a system could have, or that A and B could have, and we sum over those, what we get in the end is a correlator, and this correlator captures the entanglement entropy perfectly well. It's actually proportional to the exact configuration entanglement entropy, and indeed it grows logarithmically in time. So we're looking here at the log scale on the x-axis, yeah. So we have tenths of a tunneling time until 100 tunneling times, and it's a very nice growth that's consistent with the logarithm. And with this, we can really show that there's more going on than in Anderson localization. We are not only growing into our exponentially localized orbitals, but there's actually some crosstalk between those exponentially localized orbitals that takes exponentially long to develop this dephasing mechanism. Now, this is where we thought the story would be done, but it turns out that's actually where it only starts. Because there have always been some ideas about how stable MBL actually is. Is this actually something that would last indefinitely, or is there something that would drive MBL out of its state, out of localization, if I wait just long enough? And one of the prime candidates for delocalizing many-body localized states is what's called the avalanche mechanism, these quantum avalanches. And the idea goes as follows. So if I have a large enough system, I can always find two or more sites that are neighboring, and whose potential offsets, so whose disorder, would coincidentally actually be the same. So that means locally I can always find a system that is kind of not disordered or very weakly disordered. And if I don't have that in my system, I just make my system larger, and eventually, by chance, I would find such a system. And so in a very simplified picture, I can think of my system as a weakly disordered and a stronger disordered chain of regions that I would attach to one another. And the size of those regions, of course, is random. Some of them may just be a few sites, some of them may be a bit larger, and some of them may be very strongly disordered, some not so strongly disordered. But there will be regions that look as if they were stronger disordered, and there will be regions that look as if they were weaker disordered. And what I can do now is if I look at one of those boundaries, I could think of one part of this as being still thermal because I'm weakly disordered, and the other part of as being localized because it's stronger disordered. And if I think of my system or this interface here and in such a way, then I have to ask myself what happens in the long-term limit if this bath or if this weakly disordered region, this thermalizing region, is actually now in contact with this localized region. Is there going to be any long-term effect on the localization? And well, if you think of it in a very naive way, maybe you think, okay, I have my bath, it has a certain density of states, it has, and then I have my localized sites, they are exponentially localized, so they can't see much of this bath. And the bath then will be coupling to each of those localized sites with a coupling strength that goes down exponentially with the distance. Simply as farther I go, the weaker. And so my dephasing, there would also be exponentially weaker the farther I would go away from the boundary. It's kind of a Fermi golden rule approach where I say, okay, I have some coupling to some bath, and the closer I am, the faster I dephase, but if I just go sufficiently far away, I'm protected from this bath. Now, this doesn't take into account any kind of nonlinear effects here. So this kind of semi-classical picture turns out to be incomplete, because what happens now if I look at my very first site, and it actually delocalizes fairly fast because it's very close to this bath, is that it's not just a delocalized site, but it's actually, I have to consider it as being part of the bath, because my bath has now absorbed this one site, so it is actually larger in terms of its density of states. It has more available states that can now couple to the remainder. And that now increases my distance over which the bath can actually couple into the localized region. And this is what we call the avalanche, because it's kind of a circle of death for this localized system. So I have my bath coupling range that is initially set by the density of states. The bath will thermalize the nearest site fairly fast because the distance is very small. After that, the bath will kind of absorb the state and increase its density of states, and therefore the bath coupling range is now farther than it was before. And what this mechanism now tells me is that if I just wait long enough, my delocalization should actually speed up. It should not die, it should actually speed up. If this is true, it would also mean that if I just wait very, very long in an NBL system, eventually I should not expect localization anymore. Now, the way we probe this was to modify our toy system here by engineering exactly this interface. So we have one part of the system which is completely not disordered and the other part which is disordered. So it's kind of a very simplified approach of what we would expect to occur in a very, very large system all over. Yeah? So it's the extreme, it's a toy model. We have one part that's disordered and one part that's not disordered. And now we want to look at the dynamics there. We want to look at what happens with the delocalization on the baths, on those localized sites over time. And what we do is we start initially, and what you see is the full correlation matrix. So these are density correlations all over. Yeah? So if I have one particle that hops from one side to another, then these two sides are correlated in the densities. So that means that initially, when I have all my particles still sitting on each side, the system is completely uncorrelated. Yeah? So each side has exactly one side, has exactly one particle, so I don't see any correlations. This would be our initial state. And now as I let it evolve, I can find different regimes here. So these are on the upper left quadrant, I find correlations within my clean sites, yeah, so within the non-disordered sites, to emerge very rapidly, simply because particles like to spread around, they're not localized. I find within my disordered sites, I find that particles don't really spread around. They may go a little bit to the nearest neighbor, but they stay in their localized orbitals, so there's not much going on here either. And there are also no correlations between the bath sites, or the clean sites and the disordered sites. So I can see that these off diagonals here, they're pretty much uncorrelated yet. But when I wait long enough, I can find that, well, the bath still does the same, MBL region still does the same. But here I have also on the off diagonals, on these quadrants here, I also find now more and more correlations. And I can look at those in an averaged manner and find that there is an exponential decay. So it really shows me that the bath tries to delocalize now the localized sites. This decay here is, now we can quantify this by length. So we look at the average distance over which bath sites go into the localized sites and try to delocalize that. And if we now look at this evolution of this length scale over time, we can see that it actually speeds up. So it doesn't die out, it actually speeds up. And this is a very strong signature that indeed the bath actually accelerates in its delocalization dynamics. It doesn't die out. And we can contrast this with a small bath. So the smallest bath that one could think of would be two sides. And if I just use two sides, where I find this, that it actually dies out. Yeah? So when I have a very small bath, I don't have a density of state that can have any significant effect over the time scales that we can look at here. But if I have a significantly larger bath, I can actually find that it starts to delocalize my MBL sites. I can also directly find that these are non-linear effects by looking at least three-body correlations, because if I look at those correlations on the three-body level, I know it's not a semi-classical effect anymore between the bath and the MBL. So what we find here is correlations between bath sites and two sites within the disordered region. So essentially, these are correlators. Do particles within the localized system delocalized, conditional on bath sites? Yeah, so these are bath-driven delocalization system processes within the system and not between the bath and the system. And indeed, we find exactly that those also grow over time, and we can quantify that this actually happens. Well, intermediate disorder very fast, and very strong disorder eventually a bit slower. Yeah. What I want to emphasize is that the results here are really incompatible with this Fermi-Golden rule. So we can completely exclude that the bath and the MBL sites there can be described in any kind of semi-classical fashion here. So what does this tell us? It tells us that a localization, we know that it persists for some time. So we've seen that for reasonable evolution times of typically maybe in our systems hundreds of tunneling times, we can indeed find that there is some localization present. But we can also find that there is long-range entanglement. So all these signatures that we typically associate with MBL, they are indeed present. But we can also see that the avalanche mechanism is one that one has to take into account. So there can be situations where this arises. And now the question is a little bit on very large systems, at which point do they play a dominant role, right? So if I go to very long times and very deep disorders, at which point do these avalanche processes actually gain so much strength that over a reasonable time scale, it would lead to a delocalization. And this is something that's a question that goes, I think, a little bit beyond our experimental capabilities. Typically, what you would need there is 10,000 or even 100,000 of tunneling times and very large systems. That's something we can't offer yet. But what we can see is that this mechanism, if you isolate it well enough, you can actually demonstrate that it exists. So here these are some of the questions that we would like to answer now. For example, is it actually indeed a pre-thermal phenomenon? Does it only last for some time? That's maybe some other intrinsic timescales over which I would expect localization to happen. What are they? Can I somehow associate this with disorder, or maybe with the statistics of the disorder? I think there are a lot of open questions still. Good. I would also like to show you a little bit of what we're doing in Vienna right now, the new experiment that we're building up there, but it's also very much in the spirit of this workshop here, where we're trying to look at open quantum systems in its true fashion, not only a localized local system that is in contact with the remainder of the system in the bath, but actually systems that we can deliberately make open. And for that, the ideal tool is an optical cavity, and we are now working very hard to get this cavity as close as we can, such that afterwards we can open it in a controlled way, and we don't always have to work with an open system. The idea is that we can look at local and non-local interactions here. So we are going to engineer interactions between these atoms here and through light. So any of these atoms now can essentially exchange virtual photons for non-local entanglement generation, and we can now engineer these interactions in a way that we can drive it towards certain states, very much in the spirit of Jamir's talk from yesterday. And what's also very interesting about the system is that we can combine this with readout techniques through the cavity. So for example, we can measure the local magnetization in a non-demolition way of certain subsystems. So by microscopic control, we can bring certain atoms in and out of resonance with the cavity, and therefore only read out parts of the system in an arbitrary basis, essentially. Also, a very nice perspective for the system would be to combine now these non-local interactions with local couplings again. And for one way to engineer this would be to bring these atoms again into Rydberg states, or you can also work with multiple pumps to generate local interactions. There are several ways how one can combine this with local interactions. So we have these programmable non-local interactions, we have these readout techniques, and we have local interactions in the system. What we're working on right now is to get the system here online. Up here, okay. There we are. So one important factor for us was to get this as close as possible, and for this we chose to use optical fiber cavities. That's not something we've invented. Many groups work on this also here in Paris, for example, Jakob Reiche, but also Bonn, Meschede, and others. And what's the big advantage of those? That you can have very, very small mode volumes, which brings you to very, very high cooperativities, and therefore coherent interactions between these atoms. So this is what they look like, these fiber cavities. They have a optical fiber tip here with a diameter of just a bit of over 100 micrometers, so very, very thin. And then here at this very tip, you can curve this, you can machine this surface to have a curvature, and then you apply a high reflective coating, and then you really have a very small mirror surface with a high curvature that generates you a very small mode diameter in which you can then place your tweezers. This is what they look like under a microscope. This is what they look like in real life. We had several iterations until we really got it right, but now we're very happy with the result of these cavities. So this is a damping structure here. These are the ferrules that mount these cavities, these fibers, and within these ferrules we have these optical fiber cavities, and then here is the very tip of the optical fiber, the cavity. This is what it looks like when we shoot on glass, and then afterwards you get these very, very little dips, and this gives us then the tip of the fiber. We've been able now to reach reasonable parameters here, so there's a coupling strength of 300 megahertz, around 200 in our case now for the latest generation of the fiber cavity. We have a cavity decay rate that's on the order of 40 megahertz, and what this gives us together is a cooperativity on the order of 100. So indeed, very, very far in the coherent regime. This is our setup, what it looks like. So we have rubidium atoms that we load here. We let them fly over here in the main chamber where then the cavity setup sits in here. And then we can generate a tweezer array. This is the light of the tweezers. We load them from the 3D mod. We load them in the dipole trap. We also have some first tweezers here, which are still on resonant light, but we're very excited to very soon now also put the atoms in those tweezers. And then the next step will be that we transport the atoms. Right now they're right next to this cavity. We would move them down in the cavity, and so there's a few last steps to be done. But I think we've made a lot of progress towards this goal to actually having this tweezer array coupled to this cavity. And there's one other experiment that we are building, which is not quite fully in the spirit of this talk, but I just want to highlight that we're also working on this. It's more on fermionic systems and the quantum graph microscope, where we want to go beyond the standard, the typical square lattice geometries. We want to explore different geometries, and we want to also load the lattice with tweezers such that we can use these beautiful initial states that I've shown you earlier with one particle per lattice site in a more versatile way. And for example, also pick more sites that would be empty or others that would be full, and not only full 1D systems. So this is the system that we are building here right now. We've recently closed our vacuum system, and now we are working on getting lithium in there. Latest status right now. Good. The goal for the second experiment is going more towards topological systems, so a little bit away from here. But if you're interested in this, I'm happy to talk about this as well with you. There's a team that I'm working with at Vienna. So, in particular, highlight the cavity team here that I presented here: Johannes Schabauer, Stefan Ruszynski, and Franz Silva-Teruka. And I want to thank all of you for your attention.
Thanks for the nice talk. I have a clarification question. So what was your argument about the creation of weakly disordered region and highly disordered region? Can you clarify?
Yeah. So if you have a large system and you have disorder, that means that the offset on each side is arbitrary, is random. And that means if I have just a large enough system, I will also find two sides that are next to one another that have the same or approximately the same offset. And if I make my system even larger, I would find three sides that are next to one another that have essentially no offset. And if I make my system large enough, I would have a subsystem of any arbitrary size that has a number of sides that are not disordered. And I think this is just the argument that in any large system, I will always have some region that is not disordered. And a not disordered region is thermal. And a thermal region can delocalize a disordered region through the avalanche mechanism. And therefore, we should expect that over very, very long times, and the scaling of those time scales is an open question. Over very, very long time scales, I would expect that this local thermal region can always delocalize the rest of the system.
But my doubt is that, the probability of having a big region should be, it's exponentially small in the size of the region, right? So it doesn't seem that it's so likely that you find this big chunk of weakly disordered.
The question is, what's big, right? So we've seen 6 should be enough.
Okay.
Let's say I need 6 sides, and there is a system size that has these 6 sides, right? Yeah, I think that's the argument. You just have to go large enough until you find the size that you need.
Okay, thank you.
So, related to this question, in the usual argument about avalanches, according to the strength of the disorder, you have either that it spreads or it stops. Do you see this two regimes? Or?
So we've been working here in the disorder regime that, according to the traditional perception of MBL, would be deep in the MBL region. Now, over recent years, the critical disorder strength has been pushed to higher and higher values, so we don't really know what is critical. Now the calculations, they show you that MBL, the critical point should be so high that it's completely inaccessible. There's just hundreds of, or even more of the tunneling, right? So we've been working in here typically with, I think, for the avalanche experiments at around 8 or 9 times.
So you're always in a regime where the avalanche goes, essentially.
Yes, yeah. Well, if you would ask people 5 years ago, they would have said there should not be any avalanches anymore. They are only the critical regime. Now, I think the perception changes, or the expectations are changing a little bit, that maybe there were also see avalanches, and indeed we actually.
My question was more on the experiment. Do you see a regime where it slows down and it stops, or?
No, we don't. Yeah, with a smaller bar. With a smaller bar, we see that.
But irrespective of the size, there should be a regime where the disorder stops it. Yeah.
No, we would have to go to even stronger disorders that are not accessible. Yeah, so we can go up to 10 or so, and going beyond that means that the disorder strength would kind of bring you out of your nice Hubbard model, and you start to mix higher bands, and then things get a bit messy, and we didn't want to. It's difficult to interpret those things.
So, maybe you've shown that, or maybe it's a little bit more tricky.
when you see this crossover into, let's say, delocalization because of the avalanches, can you have a plot of entanglement entropy that crossovers from non-thermal value into thermal value? So you were talking about an acceleration, right?
Yeah.
Of the inclusion of
Yeah,
localized site into the back. But you could also see that with your initial point, right, that you see entanglement entropy separating at non-thermal value.
No, it goes up to thermal value.
So you see the crossover.
Yeah. I haven't shown those data, but you can also do that.
So it does up and then goes up, or it just smoothly going into the
Well, side by side, it goes up to the thermal value. First the first side, then the next side, and so on.
What's the interaction? What's the interaction? Just
Here's around three times the tunneling.
so you have double occupancy and more, right?
Yeah.
I mean,
You've seen the histogram at the beginning, right? There's like some 1, some 2, some 3.
what's the maximum occupancy?
I mean, in principle, n, but that doesn't happen very often. I think typically the chances
Okay.
to see 4 sides on a 4 particles on a side are already like % or so. So there's not much more than 3.
So just related to the disorders experiment that you did, do you have like a static disorder or is it like time dependent?
It's static, yes. And we always average the data over different disorder patterns.
So basically every measurement is with a different disorder pattern. And then if you, for example, like would the physics change if you have time dependent disorder within one realization? Or
Yeah, you could. I mean, essentially it's a driven system then, so that would change things up significantly. We haven't studied that, but one could also do that. Yeah.
On the avalanche, I mean, you're working still with a 12-side system, right? So did anybody do, because you arrive at 100 and you see that your correlation is basically spread to 2 sides,
Yeah.
right? So did anybody do some numerics to see whether it actually continues after 2 sides, you get to 3, 4, 5 for longer times?
So in the experiment here, it was difficult to go to more than a few hundred tunneling times experimentally, but we did numerics on the system because 12 sites we can still do ED on that, and we see that it actually goes on. So this is just the beginning of the effect.
And it finally entangles, let's say, delocalizes over
Yeah.
the test.
Eventually the whole system. But that's something we weren't able to probe experimentally. It's mostly actually a problem of post-selection here. So the problem is that if you wait long enough, these timescales in the system are fairly small. So the longest times are actually hundreds of milliseconds, even a second or so. And in order to keep the system closed or unitary, what we need to do, the main decoherence mechanism in the system is particle loss. And after a second, the chances that we lose one particle start to be significant. And so the post-selection rate that we have in the system starts to go down. And so we couldn't really go to much longer times. That's a technical problem.
But indeed, but could it be like particle loss, like something that affects like also this thermalization? If you increase the belts, somehow you also increase. I mean, I would expect that it's either particle loss in the ergodic part and in the non-ergodic part.
No, it's not. We can actually check that the system is still coherent after these long times. We can even measure the purity of the state, and we see there's no decay there. So it's simple. Once we post-select on the particle. Of course, if the particles are gone, then nothing is pure anymore. So we have this one loss mechanism, and if we compensate for that, the system remains unitary. Yeah, it's standard practice. Superconducting qubits with all time. A lot of people do this. I found the two, I suppose. I don't know. I think so. No,
Sorry, is it?
You are also post-selecting on atom loss that you would have. Okay, I think that's a no.
No, not
Okay, some of the TWISA experiments do that.